We're going to talk really briefly about four different versions of a script and why one of them seems to be really useful. One of them is almost useless, and the other two are, I could see uses for them, but there's a clear winner when it comes to these four scripts. Now, the question is, so you create a variable using the length with the position as the argument. Now, what this does is, remember, most important thing, well, I shouldn't say most important thing, but one of the key concepts with Vex is that it runs simultaneously over over all of your points in your geometry at once. So what's happening is every single one of these points, I'll turn them on so we can see a little better. Every single one of these points is executing this script at the same time. And basically it's taking its position and it's saying about how far away are you from the origin. That's what the length function does. It takes a point's position, it looks at the origin, and then it measures that distance using some vector mathematics. Really cool stuff. So you can imagine if we look at, and actually we can kind of demonstrate this, because if we turn on point numbers, and let's actually just temporarily let's decrease our number of rows here. We'll just do like a 10 by 10. Just so we have fewer things to work with. But if we kind of think about this, we would expect these points right here in the middle, 54, 44, 45, and 55, to have a pretty small d value because they're so close to the origin. Now, and these points out here, 90, 0, 9, and 99, we would expect those to have the biggest d values because they're the furthest away from the origin. Now, one thing we can do is I'm going to comment out the rest of this script just temporarily. And this is something that I recommend doing when you're learning scripts is go ahead and write your value to an attribute. So I have this variable d, and what I can do is I can make an attribute with the @ sign. Well, let's actually go through this one by one. So we want it to be a float, so that's what the F is for. The @ sign says we're making an attribute, and d is the name. So we're making an attribute named d. Now we're setting it equal to the variable d. But I think one thing that really confused me early on was I would be like, well, wait, I already have d. Why do I have to make d again? Well, here we're making the attribute d. With this d up here, this was just a variable. And remember that when you make an attribute, that is going to go onto your geometry, and that attribute is going to be accessible further down the stream. So you can kind of plan ahead which parts of your data that you're creating, your information, that you want to have access to later on down the stream. The problem is that does add more to your memory. So if you don't have to make an attribute, it's best to not do that. But when you're first learning, it's really useful to go ahead and write this out. So now if we look at our geometry spreadsheet, we have a, actually I'm going to make this background darker. I just think it's easier to see. If we look at our geometry spreadsheet, we have a new attribute here named d. And just like we predicted, remember how you can sort by the smallest and the largest? So the smallest d value goes with 44, 45, 54, and 55. And sure enough, those are the points that are closest to the center. And the biggest d values are coming from 99, 90, 9, and 0. And what do you know? Those are the four corners, the points that are the furthest away from the origin, or the center. So it's all working how we would expect. So now I'm going to go ahead and get rid of this, just so it's not confusing. So now we're adding a scale value. Now starting at 0 basically means that uh, I've now effectively set all of the d values to 0, so we don't want that. Let's try 1 maybe. And then we'll finish it off. So multiplying anything by 1 doesn't change it, right? That's the identity property, I think. Or no, it might be something else. But anyway, you know from mathematics that multiplying anything by 1 means that it stays itself. So if our scale channel that we've created here is 1, then that means that this is not changing. And then we're saying at p dot y, so we're accessing the y position, and we're saying we want that to equal the sine of whatever your d value is. So let's take a look here. So interesting. And I'm going to turn off point numbers and increase the resolution of my grid so that we can see what's going on. So kind of an interesting situation here. Now, if you think about what's going on, it does make sense, because what sine does, remember the sine function, if you remember from mathematics, let's actually really quickly, I'm a math tutor as well, so I can't help but get into the math behind it. And I know a lot of people hate math, but it's actually really useful. So this is what the sine function looks like. And if we look at what's going on here, it starts at 0, and then it goes up to 1, and then back down to 0, down to -1. See, it ping-pongs kind of back and forth. And because so many things in our world behave in cycles, right? It goes, think of the moon, for example. Maybe a value of 1 could correspond to a full moon, right? The full effect. And then a value of -1 might be when the moon is completely gone. And then your 0 would be like your half moon, right? So it's like full moon, it's waning, 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 half moon, waning, crescent, right? It's all crescent throughout here. Boom, it hits the bottom and you have no moon, right? Or what's sometimes called a new moon, when you look in the sky and you can't see the moon. Then it's waxing, 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 until it gets to half moon again, waxing, 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 getting more and more moon until we get to the next full moon, right? Here's, you don't want to be a werewolf at these points, right? Here and here. And because and think about that, the waves of an ocean, or it really doesn't take that much imagination to realize how much of our natural world is controlled by these cyclical patterns. And so that's why you'll see the sine function all the time when you're doing visual effects work, because a lot of times we're trying to model something in the natural world. And because these mathematical functions show up in nature all around us, we can use them to create more organic-looking natural phenomenon. So the main thing that I want to really point out with this video is that the sine function is going to take any value and it's going to spit something out between 1 and -1. So if we look at what's going on here, let's look at our y position. Oh, look at that. The biggest y position is basically 1, right? 0.9999. We can basically round that up to 1. What do you think the lowest y position is going to be? That's right, -1, right? Because sine takes a value and then it gives us between -1 and 1. So now, if I were to go ahead and scale that by 2, right? So now, well, it didn't work exactly how I expected it to. Let me think why that is. Yeah, because we're multiplying it before. We would have to multiply it after to get the effect that I was thinking of. So just erase that last 15 seconds. We don't want to worry about that right now. I don't want to get too confusing. But for now, let's just start with a scale of 1. But now the question is, why do we use at p dot y? Well, we could use actually whatever we want. Let's try at p. So I have this switch node here. it disappeared. What the heck happened? That's so weird. It just disappeared. Is our script broken? No, our script is actually working exactly as we would expect it to. It's just that something kind of weird's going on. What happened, if you notice, every single point has the same value for its x, y, and z position. Now let me go back to the original example, 0. Here, if we turn, I'm going to turn this, I'm going to bypass this really quickly. So here, notice that all of our points have these different x and z positions, but they all have a y position of 0, right? Because it's flat on the ground right now. Now, if I introduce our p.y script, now the y values are changing, and that's what gives us kind of that cool, like, wavy kind of motion. But my x and y's, let me do that real quick one more time. Watch the x and z values of these points. They're not going to change. See, I'm not changing them. So what's happening is all of these points, they're staying where they are as far as their x and z space. They're just adjusting their y. So when I switch over to this node here, which is using at p, what it's really doing is it's saying, okay, I'm setting my x position, my y position, and my z position all to that same number that it's calculating via the sine function. So if we zoom out, we might be able to find it, but we might have a hard time. Let's see if we can. Yeah, look at that. That's kind of weird. We created a diagonal line. But that's because all of the points now exist, a bunch of them stacked on top of each other. Do you see how point 166 and 183, they have the exact same x, y, and z values? So they're actually on top of each other in space. I can illustrate this a little better if I decrease the resolution of my grid a little bit. So let's do 10 by 10. And here you see how we have a bunch. It might be kind of hard to see, but for example, here we have a bunch of numbers on top of each other. There's a 65, and then I see a couple numbers underneath. So it's not that our script isn't working. It is. It's working totally fine. It's just that it's not that useful. I mean, I guess it is if you wanted to create a straight line, but there's better ways to create a straight line than this. Okay, so at p, you know, it's a cool effect, but it's just not really what we would. It's just not that useful. It's not as useful as the this version of it. All right, let's see what happens when we use p.x. Well, my geometry disappeared again. That's annoying. But not really. We kind of get this weird situation here. Now, why did it do this to our geometry? Well, let's think about this. So, effectively, what's happening is it is taking the point's x position and setting them equal to the sine value that we get by feeding it this d attribute. So if we look at these points here, we get a bunch that kind of stack on top of each other. And if we bypass this node really quickly, we can kind of start to break down what's going on. The x direction is here. So we would expect this script to kind of affect the points in, here. If we look at it from this angle, it's going to affect the points left-right positions. So sure enough, they all got put into weird places. And let's actually let's decrease the resolution again so that we can see what's going on here a little better. So what exactly is happening here? Well, um, if we look at, I'm going to make the the D an attribute so that it's visible again. So we've got these values here, but notice that a lot of these D values are the same, right? So for example, points 7, 11, 13, and 17, and number 6 all have a value of 2.5. So the sine function is a consistent, well, it's a predictable function. If you feed it the same value, it's going to give you the same output every time. So for example, if you feed sine a value of 0, the sine function is going to give you a output of 0 because the sine of 0 is 0. I know it's a little bit complicated, but all that to say is that if we give this d value to the sine function, it's going to give us the same result. So what we're effectively doing is we are stacking these x values on top of each other. And that's kind of creating a little bit of this kind of distortion here, where some points are actually on top of each other. And if we do it in the z, you're going to see we're going to get the same exact effect, but in the opposite direction. You see it's going this way. So the long answer to this question is that there's no reason why you need to use at p.y. It's just that these other results are a little bit not desirable, I would say. It's kind of tough to know what to do with this. Now, one way that we could make this work, I'm trying to think here. So, I guess one way we could help this, let me think for just a second. So, let's comment this out. I just want to see here. Let me go back to this one. So right now, yeah, because the reason why this is happening is because if we think about the origin, so point 12 is at the same place as the origin, right? So it makes sense that it's, you know what? What I'm going to do is I'm actually going to call this. I'm actually going to call this length so that it's easier to kind of understand. So if we look at the length, point 12 is 0, which makes sense because it's right on top of the origin. But with here, all of these points right here, if we kind of measure them, well, actually, sorry, if we take these points, 7, 11, 17, and 13, they're all exactly the same distance away from the origin. So that's why they have the same d value. So in order to not get this problem, what we probably want to do is we need to introduce some randomization. So what we could probably do is create a random number based off of your point number. So we'll call this float randomizer. And then what we can do is go ahead and multiply by that. And let's see what this gives us. It didn't really work how I wanted it to. Let's see what happens after we multiply by the randomizer. So that helped with the length attribute. Now we don't really have the same one, uh, but we have a little bit of a problem because it's moving things randomly, so we're getting kind of overlapping lines. I might have to think a little bit harder about this. If I wanted to adjust, I think what I would do is I'd probably I think what I would do is I would get a where I'm actually changing the x value. I would create a dampener um, channel here, and I would just make this like 0.01. That's not working how I thought it would either. Oh, because we'll do plus, and then we'll make this like, well, just 1 for now. Yeah, okay. So this is behaving a little bit more predictably. Let me actually increase the resolution here. And what we can do is take this down. It's still moving too much. 0.01. Well, I mean, it's working, but it's just. I probably don't need this much resolution. Is probably what. Oh yeah, I did 500. My bad. Okay, here we go. So if we do like 0.05, yeah, there we go. So see, we introduced a little bit of random noise in the x direction. Now, if you notice, the further away from the origin, the more extreme our effect is. But what we could do is we could multiply this by @time, which is a global attribute that you have access to. And now, or actually, we don't want to multiply. We want to add time. And now, if we animate, it should wobble, but it's not. I think. Oh, I think actually what we can do is multiply it in here. I would expect that to change over time. Let's see. So if I comment this out, let's see what's going on. So we have our length, and oh, because I'm not, yeah, because so one thing that you can run into is I'm changing this length attribute, but remember we're using the actual variable here. So so what I probably should have done is left this here and then done this. So d equals, or let's multiply it, or let's add it to time. That should give us our. Oh, let's see, maybe multiply. There we go. I finally got it to work. So sometimes it is a little bit of trial and error. Once I study this example a little bit better, I'll be able to explain why it's working. But we do finally have our wave-like motion in the X channel. So that could be kind of cool if you want some subtle movement, right? Actually kind of like that. And we can take this up to 0.1 and get some even more extreme movement. And in fact, it looks like it's getting more extreme over time. Like if I scale this to like 2, oh no, it's kind of oscillating between the same position. So if I zoom really close here, you can see this point, it's ping-ponging back and forth. Now remember my example with the moon, right? So this would be like, um, you know, if we just take one point, like, let's just take this point right here, 1760. What it's doing is, see here would be like new moon, and then it's going through the phase, half moon, and then boom, it hits full moon, and then it swings back again. See, everything's moving in a cycle. And the reason why it's doing that is because we're using our sine function to do that. So anyway, I hope that answers your question. I know it's a little bit more than we were probably hoping for, maybe, but I think that it's still useful to understand this stuff, really understand the sine function because you're going to use it a lot, and I think it's really important to understand what it does so that when you are changing things with the sine function, you realize that what you're doing is you're creating a cycle, right? So anyway, take care. Any more questions, hit me up.